Welcome to Empowered Learning. This video will be about the concept of work and modeling the concept of work using integration. So if you've taken a physics course before, then you should have ran across this concept of work before. And work is just simply just a force acting on an object over a certain distance. And we call work specifically the product of that force and that distance. Now, the way in which we model work, we use Newton's second law, which basically says that force is equal to mass times acceleration. And if you remember from first year calculus, acceleration can be also expressed as the second derivative of position or displacement. If you're talking about distance, then of course your S of t function can be interpreted as distance. And so we'll just assume that here, even though, it can be displacement. So because of that, we know that force can be rewritten as the mass times the second derivative of the displacement of that object at any given time. Okay. Now, with this particular formula for force, and thus if we were to take this formula and multiply it times the distance, it would be the formula for work. The thing is that we are considering that this distance that's modeled by S of t of that object is being acted on by a force where that force and the distance are all pointing in the same direction. Okay. If you're familiar with how we look at things as far as vectors are concerned, we are taking the r vector and we are taking the force vector, where r vector is going to be the distance or the radius vector or whatnot. So we're taking that, well, really we should say d vector. So let me just write it like this. So we're taking a d vector and we are taking a force vector, and we have the force vector acting on the d vector. So we would probably want to write it like this. Then one of the things that we know is that if those two forces are acting in the same direction, then the angle or direction angle in between those two vectors would be 0. So in a case like this, where we're not given any inkling of, hey, what's the direction, we're assuming that the force and the direction in which the object is traveling are all going to be in the same direction. Okay. But again, what happens if our object is kind of doing like this? Let's say if it's not, going the same direction in a straight line, or if it has something going on like this, and let's say your force at that particular time is acting on that particular object at that point that way. Okay. Then from that perspective, how do we deal with that? And so this is why we try to use calculus, and in particular integration, as another means of being able to model work. And so again, it says the definition of work above only deals with force when force is constant. Okay. And that is to say the force is constant and moving in a straight line. But how do we deal? How do we write a formula for work done on an object when the force is constantly changing? So here I've actually modeled it to where the path of the object is changing, but I could also have it to where let's say the path is this straight line here, but the force on which is acting on that particular object changes. So we could look at it that way too. Okay. And this second model here is going to be the one that we're going to use. So again, how are we going to deal with that? Well, we're going to use calculus, and in particularly integration, to be able to do it. So to get straight to the point here, we know that if force can be modeled and expressed by a continuous function, meaning that whatever force is being applied, it may not be constant, but there may not be any breaks in that force acting on that particular object at any given time. So if we can make that assumption here, then that means that we can express the force as some function of x, and thus we can look at the area under the curve of f of x And one of the ways that we could translate that is the actual work of that particular force on some object for a certain distance. And of course, that distance will be from some x value A to another x value B. Now from Cal A, how we actually write that is if we look at this in its pure form, we're saying that, hey, I want to look at the sum of all the little small strips of area that's going to be under the curve of some function f of x from x equals a to x equals b. Okay, so let's say if we take a small little strip here and we say, all right, well, if we do the work for that instance when this is x of I, and we add up a bunch of those together, then that would actually be what the work would be. But the thing is, with that strip, we would want the width of that strip, and I'm just going to draw it like this here. We would theoretically want the width of this particular strip here to be a length of dx, meaning the smallest possible positive change in x value. Okay. Now, in order to do that, theoretically speaking, we know that n, or the number of these little strips that we would try to stuff in between from x equals a to x equals b, would be an infinite amount. And of course, when we express it that way, then we're talking about a Riemann sum, and in this case, an infinite Riemann sum. And so what we want to do is to say, how are we going to study the behavior of the area of these little strips as the number of these strips approaches infinity? And of course, this limit notation of limit as n approaches infinity implies that, hey, we want to study the behavior of the Riemann sum as the number of strips tends to go toward infinity. And by definition, we know that this limit operator and summation operator come together to be this infinite summation sign, or what we know as an integral. Okay, so in general, all I'm saying here is that if we can model our force by some continuous function, then all we have to do is take the definite integral of that function from x equals a to x equals b, and we will know the work for that particular function. Okay. Now, some other side note things that are important for us as we begin to work on and specifically model problems that have this concept in it. The first thing is that force is going to be measured in newtons if we're talking about international units. And of course, a newton is just a kilogram meter per second squared. Or if we're doing English units or imperial units, that will be in pounds. Okay. So work is going to be measured in joules, which is just a Newton meter, or newtons times meters. Of course, in imperial units, most of the times it's going to be measured in foot pounds. Okay. Now, Hooke's law, or this is basically the law that tells you how force acts on a spring. We're going to use this a lot as well. And so the force required to maintain a spring stretched x units beyond its natural length can be modeled by this function f of x that we're going to refer to. And simply put, Hooke's law just says that the force is directly proportional to how far you stretch the string past its natural length, where k is going to be that spring constant, x is going to be the distance that the spring is stretched beyond its natural length. Okay, and of course f of x is going to be the force. Now, if we look at some pictures here, we'll see figure A is just our spring in its natural position. So of course, in that case, x is just going to be interpreted as being 0. But if we stretch it, then x is going to be some value beyond 0. Okay. Now, note that here, if we were to go in the opposite direction, and let's say we would go negative x units in here, of course, the value for x that we would use would still be non-negative because of the fact that we are referring to this as a distance. And of course, we know distance can be non-negative. So even if we were compressing the spring, the same amount of force would be exerted if we were stretching the spring. It's just the direction in which the force goes in will be opposite. All right, and so the only thing that I'm trying to show here in this picture I've drawn is that the concept of work being area under the curve of a force function is just like in Cal A when we talk about the area under the curve of some function, just some regular function in Cal A. And so because we can model it like that, we use integration and in particular definite integrals to be able to do that. And because of that, we see that the strip that we have for the area under the curve from Cal A, we know that each strip, its height, or in this case, its length here is going to be f of x sub I. And of course, its width here is going to be delta x. Similar sort of thing here. The height of our function is going to be what the length is for that strip. And of course, delta x is going to be the width. Okay. And of course, with work, that f of x sub I is going to be equal to the force, and that delta x there is going to be equal to the d for that small strip there. All right, so let's do a simple example here. And so we want to see or find the work done if a constant force of 100 pounds is used to pull a cart a distance of 200 feet. So for this one, this is relatively easy here. All we're really doing is taking the information, and since we have a force that's given to us in pounds and we have a distance, then all we have to do is multiply the force and the distance together. And we see that 100 pounds times 200 feet is going to give us 20,000 foot-pounds. Okay. So when you're given that constant information, then of course all you have to do is just multiply the answers together. Now for example 2, we see that the following graph below that I'm showing you here is the graph of some force function, big F of x. And so the force increases at a linear rate for for a certain amount, and then it goes constant. Okay. And so once it reaches its max value, it's going to remain constant. And we want to know how much work is done as that distance traveled from 0 meters to 8 meters. Okay. So in this case, this problem is relatively easy too, because of the fact that if we look at our graph here, we know that we can divide the area under the curve of our force function, since it is continuous, into 2 separate areas. So as long as we can find the area of this right triangle and the area of this rectangle, add them up, we're good to go. Okay. Now note that I could actually go here and algebraically figure out what this line is going to be and figure out what this is, and we would still get the same answer. But since we already know geometrically what the area under the curve is, at least we know formulas for it, it's much easier for us just to use geometry to do this versus using calculus. Trust me, we'll have enough calculus to do. So whenever there's an easier route to get to the answer, we want to go ahead and use that. So in this case, we see that we have area 1 is going to be a right triangle where our base is going to be 4. Our height is going to be 30. Okay. So here, and I just say the base is the difference in between 4 and 0. So that's why I have this. And the height is going to be difference in between 30 and 0. Okay. So we have that. And of course, for this rectangle, we have a base of 4 and a height of 30 here as well. Okay. And so that's why you see 30 minus 0 here, 8 minus 4 there. And of course, once you do all the math and, for each term and add it up, you see that you get 180 Newton meters, or another way that we could say that is just 180 joules. Okay. All right, let's move on to example 3. So this example will be the first one where we actually start to use some calculus here. And so we are given that it takes 2 joules of work to stretch some spring from its natural length of 30 centimeters to a length of 42. Okay. Now, if you remember, we only look at how much we either stretch or compress a string from its natural length. So we don't care about the 30 meters part. What we care about is the difference in between the 30 meters and the 42 meters. And of course, 42 minus 30 is going to be 12. So that distance that we're going to be looking at is 12 centimeters. Okay. And in terms of meters, of course, that's just going to be 0.02 of a meter. Okay. So we're just going to keep that in mind. So the first thing that we want to do here is we want to find out how much work is needed to stretch this spring from 35 centimeters to 40 centimeters. Okay. Now, since we're dealing with a spring, we have to model the situation by Hooke's law. Okay. And of course, Hooke's law basically says that a force is equal to some spring constant times x. And note here what we have already been given the value of the work, or the amount of work to do that. So we can use what we know about us modeling work in terms of a definite integral to be able to figure out what is our spring constant, because that's the one thing that we don't have for this specific situation here. Okay. We know how far the spring stretches. We know what the work is. So we know the work, we know the distance. What we don't necessarily know is the force per se. Okay. And so here, since we just have an x here, the only thing that we really don't know is what that constant is. So we need to find it. So here, in looking at that, our work is going to be definite integral from x equals a to x equals b of kx dx. And of course, k is our constant. And again, like I said before, we only care about the difference in between the natural length and where it stretches out to. And we know that this work here could be exactly 2 joules whenever we stretch the spring 0.12 of a meter from its natural length. So this is letting us know what our limits of integration are going to be. A and B are going to be 0 and 0.12 or 12 100ths of a meter, respectively. And so then we throw all that information in. We have our 2 joules. We have our limits of integration here. And from that, we just need to find out what our constant is. So we take the antiderivative of x, which is just going to be 1/2 x squared, and we evaluate that from 0 to 0.12. You see the math is done there. We end up with k divided by 2 times 0.0144, and of course all that's equal to 2. So we take this, rearrange it, and solve for k, and we see that in fraction terms we have 2500 over 9 newtons per meter, or about 277.78 newtons per meter. Okay, so this is what our spring constant will be. So now that we have our spring constant, we know that our f of x is just going to be 2500 divided by 9 times x. And so now we know for any distance that our spring is being stretched from, we know how to actually find the work that it takes now, because we had the one thing that we were missing. So here, now that we know that info, we know that 35 100ths of a meter is going to be only 5 100ths of a meter beyond the natural length of 30 100ths of a meter, okay? Or 3/10 of a meter, I should say. So here we know that the difference in between the natural length and 0.35 of a meter is 0.05 of a meter. And where we stop is at 0.4 of a meter, which is about 1/10 of a meter. And so we use the 0.05 and the 0.10 as our limits of integration now with our newly found integration constant. And then it's just a matter of taking the antiderivative of x, using the net change theorem from Cal A to evaluate that result. And then we figure out here that it's just a little over 1 joule, okay, that it takes to stretch that spring from being 35/100ths of a meter from its natural length to 40 or 40/100ths or 4/10ths of a meter from its natural length. Okay, so that is our part A. So part B for this problem, we want to know, well, how far beyond the spring's natural length will a force of 30 newtons keep the string stretched? Okay, so again, now that we know what our spring constant is, which is this 2500/9, and we were given information about this force here, we know what we're trying to find is how far beyond the spring's natural length. So what we want to know is distance here. So we have force. Force is equal to K times X. We have this. What we need to find out is what X is. So here we let f of X equal to K times X. Plug that in. We know that f of X is going to be 30 in this case, and just rearrange it to find out what X is. And we see that we get 10.8 centimeters. Okay. All right. So this should be relatively easy. Again, whenever we have work, we know what formula that we're going to use. So it's just a matter of trying to figure out what information that we don't have and coming up with a strategy to find it. And then, of course, if we get follow-up questions like this one, we see what it is that we can do, and it's relatively easy. All right, let's go ahead and move on to our next example. All right, so in our next example here, we have a bucket that weighs 4 pounds and a rope that we're going to assume has negligible weight. And this bucket is basically being dipped in a well, is being filled up with water, and then it's going to be pulled up to the top of the well to get. Okay. Now, it turns out that this bucket itself weighs about 4 pounds, and we can hold about 40 pounds of water in the bucket. Okay. So because of that, if the bucket is full, it's going to be at the point where we are down here and we're ready to start to lift it up. It's going to weigh 44 pounds. Okay. So that's going to be the initial force that we're going to be dealing with. We also know that the well is 80 feet deep, and that's important to us because unfortunately we have a hole in our bucket. Okay. And because of the hole that's in our bucket, the water is leaking out at a rate of 0.2 of a pound per second. Okay. So with that being added to the mix, we want to know how much work is going to be done pulling the bucket to the top of the well. Okay. Now, before we begin this problem, let's just look at some common sense things. Okay. Let's say if we had this bucket that was here, and let's say there was no hole in the bucket. Okay. Then of course we would have this 44 pounds that we would have to pull up all the way to the top of the well. And of course, the force or the weight of that particular bucket would be the same as you continue to work to get the bucket up to the top of the well. Okay. Now, because of the fact that there's water being leaked out of it, the bucket's going to weigh less the more we pull it up. So by the time we get up to the top of the well, which is going to be at 80 feet here, the bucket is going to weigh less than what it did originally when we started to try to pull it up. Okay. So the other thing that is important is that they tell us, and this is important, but it's very subtle. They tell us that the rate in which the bucket is leaking is constant. Okay. So anytime we have a rate of something being constant, then by definition, that lets us know that the change in whatever that is linear. Okay. So when the rate of change of something is constant, then it means it came from a linear function. And we know that because if I take y equals mx plus b, and if I take the derivative of y, which is instantaneous rate of change, we know that the instantaneous rate of change would just be m, which is, whatever that rate is. And of course, m by definition is slope, which is rise over run, and which is a rate. Okay. So I'm saying all that to say that before we even jump into this problem, one of the things that we know is that the force of the bucket, aka the weight of the bucket, is going to change, and it's going to change linearly. Okay, we know that up front just by all the little keywords and information that was given to us. The other thing that we know is that the force should be modeled by a linear function that has a negative slope. And we know that because of the fact that we are losing weight as we pull the bucket up to the top of the well. Okay. And so what the weight is going to be in the beginning and what the weight's going to be in the end when we get it all the way up to the top is going to be less. So therefore, we know that our rate has to be modeled negatively. Okay. So with that being said, we see that before we begin, there are a few things that we need to take stock of. And so here, since the bucket is being pulled up at a rate of 2 feet per second, okay, then we know that since it takes, we're traveling a total of 80 feet here, we know it's going to take 40 seconds for us to pull that particular bucket up. Because of the fact that here we take 80 and then divided by 80 feet and divided by 2 feet per second. Feet divided by feet per second gives you a result of just seconds. And of course, that lets us know that we need to divide 80 by 2, get 40 seconds. Okay. So just putting it simply, hey, if I was to pull it up for 1 second, I would get it 2 feet up. If I was to pull it up for 2 seconds, I would have it 4 feet up. If I was to pull it up for 3 seconds, I would have it 6 feet up. And if I keep on doing that, eventually when I get to 40 seconds, I'll have it 80 feet up. Okay. Now, again, the water is leaking out of the bucket at 0.2 of a pound per second. So if we take this amount and multiply it times the 40 seconds that we have, then of course 40 times 0.2 is going to give us 8. And so since seconds here and seconds here are going to reduce to 1, all we have left is the unit of pounds. And so we see that 8 pounds of water is going to be lost from the time we begin pulling up the bucket to the time we end it. Okay. So what that tells us is that when we start pulling the water up, we're going to be at 0 feet. Okay. And remember, we're modeling this where 0 feet is going to be right at the point where the water of the well is here. So the top of the water is here, and that's where we let x equals 0 be. And of course, x equals 80 is when we're at the top of the well and we can actually grab the water. Okay. So knowing that, come back down here. So we know that at 0 feet, force of the bucket is going to be 44 pounds. When we pull it all the way up at the top at 80 feet, we would have lost 8 pounds of that. So 44 minus this 8 is going to give us 36. And of course, this f sub I is going to be the 44. So that's the 44 minus the 8 here, that gives us 36 pounds. Okay. Now, what this means is that the longer or the more we pull the bucket up, the easier it's going to be to pull it up, because of the fact that it's weighing less and less and less the longer we pull it up. All right, so we see that the water in the bucket decreases from when x is 0 to x is equal to 80 feet in a linear fashion, and I've already explained why. So from here, all we have to do is really take the information that's given to us and form our linear function for the force, aka the weight in this case. So all I've done here is I've taken 2 points, and we know if we have 2 points, we can find the equation of a line. Here we let this be x1, y1, x2, y2, and just plug it into our formula here. Okay. Another way that we can look at it is let the x2 and y2 be the final x and y value, and let x1 and y1 be the initial x and y value. Okay, and then that's what I've done here. And so from here, and I think I think I've actually done it backwards there, but it still ends up being the same thing. So we start off, oh no, actually I haven't done it backwards. So, well, I labeled it backwards. Let me say it like that. The way that I was looking at it was right, but I've labeled it backwards. But we need to label it in terms of what the force would be. So the force will actually start off being like this, and it will end like that. So that means, we would have to have it like this here. And this should be, I don't know why I have it like that, but okay. Yeah, so the way I intended this to be here, I guess I wrote it actually backwards from what I wanted it to be. So let's see here. So what I should have done here, just to kind of make it make sense with the problem, is I should have said 36 here minus 44. Right here. And then this should have been 80 minus 0. But it still ends up being the same thing when you do that. I just decided to kind of do like this, y2 minus y1 over x2 minus x1. I decided to do it that way. Doesn't matter how you do it. As long as you keep the convention straight, you'll still get the same answer. So for here, we see that we have negative 1/10 or negative 0.1. And so since that is our slope, and we know by definition that this point here, 0.44, is a y-intercept, we could use that 44 directly into our formula here for the force, or aka the weight. So we see that our function ends up just being a negative 1/10 x plus 44. So that means our function is going to end up being that. And so now that we have that in place here, everything else is pretty easy. Okay. So notice all I have to do now, work is equal to the definite integral of my force from x equals a to x equals b. Of course, x equals a will be at the top of the water at the bottom of the well, which is where x is equal to 0 is. Top of the well is at x equals 80. And we have our function here. And then it's just a matter of taking an antiderivative of this linear function, which we have here, evaluating it from 0 to 80. And once we do a little cleaning up here and get 44x minus x squared over 20, then we use net change theorem, plug in 80 minus plug in 0, and then we see that we end up getting 3,200 foot-pounds for that. Okay. So hopefully what you're seeing here is that the more difficult part of some of these problems is just modeling what the force is going to be. Once you model the force, everything else is relatively easy. All right, so let's look at our next example. All right, so for our next example, we have this tank that looks kind of like a right triangle. and it's full of water. And what we want to do is pump out the water that's in the tank. And so to do that, we want to find the work that's required to pump the water out of this tank from this little spout that's right here. Okay. Now, we're not considering some of the resistance and other things that we would probably need to take into account if we were, let's say, like in a fluids course. Let's say if you're a mechanical engineer or civil engineer, and you were in a fluids course. We're not going to, take things like the voricity of, the water and there's something called Torricelli's law that kind of lets you know, hey, based upon the area of this particular spout, there's going to be a certain resistance that goes along with that water trying to get through it. We're not going to be dealing with all of that. Okay, so we essentially just want to know what is going to be the work to get all the water out of that tank there. Okay. All right. So the way that we are going to approach this problem here is we know that depending upon what level we are at in the tank, that certain little piece, or as I call it, a slice of water, that individual slice is going to take so much work for it to be able to get from where it is in the tank up to the top and out the spout. Okay. So we're going to look at this as just saying, hey, we're going to deal with one slice of water. And when I say one slice of water, we're going to look at a very thin volume of water and say, for that thin volume, how much work is it going to take me to get that thin volume up, depending upon how high it is up from the bottom of the tank. And then after that, we'll just say, all right, well, if I can generally model one slice of water, then I can model all the slices of water that I would use, from the bottom of the tank to the top, and just add all those slices together, or the work that's involved to get all those slices together to get all the water out of the tank. So that's going to be the approach here. So here, what I've done in this picture, figure B, is I've taken a cross section of what this tank looks like. And so I've done that because of the fact that we know that at any given time, let's say if we looked at a specific slice of water here, and I'm gonna do it by this black line right here. So let's say if we looked at that slice of water at any given time, well, it's going to be a level of X units up from the bottom of the tank. Okay. And we know that the height of the tank is going to be 6 feet. So if we are X units up from the bottom of the tank, then that means that we only have 6 minus X units left to get that little slice of water up and out the tank. So that 6 minus X there for that particular slice of water is going to basically define the distance part of the work that we need to find. Because remember, work is force times distance. Of course, in the formula, the distance is going to be characterized by the A and the B. And we're just looking at one of the very many terms that we use to get this infinite sum. Okay. Now, to characterize the volume here, notice that the thickness of the water is going to be the same as the width of the tank, which is 10 feet. Okay. We know that as far as the length of it, it's going to model what this is here. Okay. And of course, depending upon how high that slice of water is, lets us know how much of this 12 feet it actually extends across. Okay. Now, the one thing that we do know is that, of course, if the height is 6 feet, if we're already at the top, and the length here is 12 feet, then we know by similar triangles here, if we are at X feet like this, then this length here is going to be 2X, going from right here to right here. So we know that, okay? So at any given time, if we are X feet above the bottom of the tank with this slice of water, then it's going to extend out this way a length of 2x. Okay. And we also know that the width of that particular water at any given time is going to be 10 feet. Okay. So needless to say, the volume of the slice is just going to be this 10 feet times X feet here. And then that's going to be times, again, 2x feet here, okay? And if we multiply all that together, that will give us the actual volume of that slice of water at a given level of X units above, or X feet above the bottom of the tank in any given time, okay? All right, so as I just got through explaining here, you see I've also written this out. So if we got 2x for the length, 10 for the width, and our delta x for the thickness there, and that is what this particular part here will be, okay? And I think I called it x, but it really should be the thickness there. So, because I was looking at the level, but it really should be, yeah, this thickness here. So let me change that. So I'm not talking about the thickness from the bottom of the tank all the way there. I'm just talking about just that small little slice. So that would be delta x feet here. Okay. Yep, and so this is how we would actually characterize that for that one slice. Okay. Now, we were given information about the fact that this water weighs 62.5 pounds per cubic foot, okay? And we don't know what other minerals are mixed in the water. We just know that whatever's in it is going to be 62.5 pounds per cubic foot. So, and that's going to be our density, or now are going to be our weight density, okay, which is going to be weight per, in this case, unit volume. So we need that because here what we're actually trying to model is a force, okay? And in this case, we're going to need force to be in pounds. Right now, what we have is a volume, which is in cubic feet. And if we're going to have something that ends up giving us pounds here, then what we're going to have to do is use something that's going to get rid of this cubic feet. And of course, if we have pounds per cubic foot, then these cubic feet here reduce to 1, and we just end up with pounds. And of course, knowing what the weight density of the water is the thing that we need to know exactly how many pounds it weighs, okay? So here, if we take into account the weight density of the water, which is in pounds per cubic foot, and then multiply that times the volume in cubic feet of that particular slice, then again, like how I said, the cubic feet reduced to 1, and all we have left is pounds. And so we see that for a given level of X feet above the bottom of the tank, this is going to be the actual force, or the weight of that particular slice of water, okay? And so now we know that the work involved will just be this force, or the weight of that particular slice, times the distance that it has to travel. And again, we know that, I'll go back to the picture here, we know that at a particular point here, at this particular point, where X units above the tank, we have 6 minus X units to go to get out of the tank, okay? And so here we know, because of that, our distance is just going to be this 6 minus X here, okay? So from that, we see that the work is just going to be, and this is just, kind of being a purist here, it's going to be the summation of the force times the distance of all the little slices of water. And so here, this is going to be the force of the weight of the slice of water times the distance that that slice of water has to travel. And we're wanting to essentially say, let's look at all the slices of water from I = 1 to n, and we want n to go to infinity. So we want to get an infinite number of slices of water from the bottom to the top of the tank. And of course, that's telling us that, hey, we're going to look at the bottom of the tank, x = 0, top of the tank, x = 6. And so then from that point, it's just a matter of multiplying the 1250x times 6 minus x and doing the integration. And, from this point, it's just basically first year calculus. So we go ahead, multiply everything that we need to. Of course, this 1250 we can factor out, make life a little easier for us, and just multiply in that x to both terms. You see that? Take the antiderivative of both terms, and then use the net change theorem to evaluate this portion at 6 and then at 0. So we see that happen here. And then from there, we just do the arithmetic rather to just get our final answer, which will end up being 45,000 square foot-pounds. Okay. And so that would be the actual work that we would need to be able to get it out, get the water out. All right, and so actually that should just be just foot-pounds, not square foot-pounds. I don't know where I got the 2 from, but yeah, and that's because here, this first term here is just pounds, and this is feet. And remember, we're just adding a bunch of those pound times feet slices of water together. And so whenever we do this, those units don't change. And so that's why this would still have to be like foot-pounds, or as I put it, foot-pounds or pound-foot. You can switch it either way. It doesn't matter. But I think most people say that it's foot-pounds. So that's why I put it as foot-pounds here at the end. All right, so this concludes part 1 of the series on work. I'm going to record another video where we're going to go through examples where they're not going to be worked out like this. So we're actually going to model them and work them out from beginning to end, so you can kind of get a feel for how that is versus just me having everything already worked out. All right, so I'll see you in the part 2 video.